Sorry about that, guys. Okay, my calculator's on charge now, so we should be good. Okay, now that we have calculated, again, the mean and the standard deviation using, again, this pooled sample proportion, which we got as 0.023, we can start to draw our picture. So we want to draw our normal curve. Okay, so I'm going to label that. This is a normal curve with mean 0 and standard deviation 0.023. All right, put 0 in the middle, go up 1, 2, 3 standard deviations, and down 1, 2, 3 standard deviations. These are actually pretty easy because I'm starting at 0. So going down would be negative 0.023, and then negative 0.046. negative 0.069. I'll fill in the positive ones in the filled in notes that I post later. But I just want to point out, if we're trying to put our a difference in sample proportions on here, it's negative 0.11. So we'd have to keep going, right? The next one would be what? Negative 0.92, something like that. And then again, we get up to like negative 0.11. So our negative 0.11 is somewhere way down here. So there's barely any area left in the curve. But again, that would be the probability that P1 hat minus P2 hat is less than or equal to negative 0.11. Okay, so tiny little probability. Again, I also want to point out that I'm going to find that probability by finding the test statistic, which will be a z-score, and figuring out the probability that by figuring out the area to the left of that z-score. Now, I didn't actually draw the standard normal curve here. I drew the normal curve representing this sampling distribution. But they would be the same thing, right? If I labeled this 0 and then went down 1, 2, 3, 4, 5 standard deviations, I would get the same z-score, my z-score would be in the same spot as this negative 0.11 is on the sampling distribution curve, okay? So the area is the same, even though I'm not actually writing on here that that's a z-score. I'll point that in again when we find out what the z-score is, but just so you know, I'm expecting it to be between, 4, between 4 and 5 standard deviations beneath the mean, so between negative 4 and negative 5, but probably closer to negative 5. Let's see if that's true. Okay, so our general formula for a test statistic, remember, is test statistic is equal to the statistic minus the parameter divided by the standard deviation. And so I'm going to plug in, my test statistic is a z value. So let's see, I think I'm going to have enough room here. My statistic is P1 hat minus P2 hat. And I do that subtraction first. And then second, I do the subtraction for the parameter P1 minus P2. So statistic parameter, once I've actually found those two differences, then I subtract. Divided by... Okay, so remember again, I don't know what P1 and P2 are, so I just know that the difference between them is 0. So I'm using that P pooled times Q pooled divided by N1 plus P pooled times Q pooled divided by N2. And I take the square root of all of that. That's my standard deviation. Okay, so let's plug in. We're going to get Z is equal to, I'm actually going to plug into the bottom first because that takes the most space. So my P pooled value, remember I rounded to 0.109. So that's what I'm going to write down again. 0.109 times 0.891. Again, 1 minus 0.109 is 0.891 divided by 300 plus 0.109 times 0.891 divided by N2, which is 500. And I take the square root of all of that. Okay, that's the denominator. The numerator is my P1 hat minus P2 hat, which remember is negative 0.11. So I have negative 0.11. I don't have to rewrite what P1 and P2 hat are. I can just go ahead and write the difference. Minus my hypothesized difference in P1 minus P2. Again, I don't know P1, I don't know P2, but I know that I'm hypothesizing the difference between them is 0. Okay, so I work all of that out at once in my calculator, and I'm going to write down what I get for Z. So the nice thing is I just calculated what that standard deviation is in my calculator. So I'm just going to go back up and select that when I need it. For the numerator, I need negative 0.11. You can write minus 0 if you want to. I'm not going to. I know that minus 0 isn't going to change anything. So negative 0.11 divided by all of this. Hit enter, and I get negative 4.8. I could write 8.3. Let's see, but I'm going to go ahead and write well, actually, it doesn't matter. I was going to say I should just round to 2 decimal places for table A2, but negative 4 is going to be way beyond what table A2 has to offer us. So I'm going to go ahead and do 3 decimal places. Negative 4.838. Okay, so that's my test statistic, negative 4.838. And look at that. Our value of negative 0.11 is 1, 2, 3, 4, and about 0.8 standard deviations beneath the mean. That's what my test statistic represents. So I'm looking for that area to the left of it, which I know visually from this graph is going to be very, very small. If I just look at table A2, that only goes out to z-scores of negative 3.5. And it says anything with a z-score less than negative 3.5 has a left area less than 0.001. So that's one way that I could think about the p-value, that it's just going to be less than 0.0001. But I can get more specific than that. So I'm going to use that normal CDF function to figure out exactly how much less it is. So normal CDF, let's go ahead and find that. We go to second distribution. It's the second one, normal CDF. This negative 1 e to the 99th is fine to leave there. It really means that we are multiplying this by we're multiplying negative 1 by 10 99 times. So it's a negative 1 and then 99 zeros. Huge, huge negative number. You could leave it like that, or you can change it to negative 10,000. I don't really care what you do. And then your upper is that z-score, negative 4.838. And then we leave the mean and standard deviation at 0 and 1, because remember this is a z-score, which has a mean of 0 and a standard deviation of 1. Okay, so I'm going to paste that in and get my value. Let me go ahead and write down what my commands were here. Negative 10,000 to negative 4.838 with a mean of 0 and standard deviation of 1. That gives me a p-value. All right, so it has all 6 point blah, blah, blah decimals, e to the negative 7th. That means move the decimal place here to the left. Negative means left 7 times. So if I move it once, I'll have 0.6 something something, and I have to move it 6 more times, so I'll have 6 zeros in front of that 6. So 0.1, 2, 3, 4, 5, 6 zeros, and then I start with my numbers. So 6, I'm going to round, let's say 6 is fine. Okay. That is definitely less than 0.0001. It's quite a bit less. So I think it was worthwhile actually finding the exact value. You could go ahead and say that this is approximately equal to 0. This is a very, very, very small probability. So let's try to interpret that. Remember, our interpretation for the p-value is assuming the null hypothesis is true. So assuming there really is no difference between the 2 population proportions, then about this proportion of the time. So if I were to convert this to a percentage, it would be what? 0.000066% of the time. We get a difference in sample proportions of negative 0.11, or more extreme, right? Or more this way. That's so rare. We're definitely not believing that that original assumption can be true. So let's state that. Since the p-value equal to 0.1234566 is less than our significance value of alpha equals 0.05. Remember, whenever your p-value is less than your significance value, you reject the null. We reject the null. We don't believe that original hypothesis could possibly be true. So to put it in context, we do have convincing evidence And then we could state that P1 is less than P2 and put that in context, but I'm actually going to use the original statement from the question. So we have convincing evidence that Black and Hispanic females are underrepresented in STEM programs. That's what it means for the proportion of STEM Black and Hispanic females to be less than the proportion of non-STEM Black and Hispanic females. So that Black and Hispanic females are underrepresented in STEM programs. Okay, done. That is our hypothesis test. I'm going to make another video for the big ideas that go with that.